Let us talk about permeable horseshoe obstacle in fluvial environment. I will start by a series of acknowledgement of country, acknowledgement of my co-worker and co-author, acknowledgement of a number of people who have assisted with the project. My name is Hubert Johnson. I'm based at the University of Queensland in Australia, and I live in the city of Brisbane. This talk is about inland Australian waterways that are characterized by extreme conditions, ranging from long droughts to massive floods. On the long inland waterways, a number of historical heritage hydraulic structures were built by indigenous Australians, including weirs, fish traps, and reservoirs. And in this talk, we shall focus on rock fish traps, with a few examples here. These rock fish traps were typically located inland in the eastern half of Australia, in particular the Murray-Darling Basin, shown in with the red line, and the Lake Eyre catchment, highlighted with the orange-yellow line. They presented some analogy with horseshoe rock waterfalls, as well as horseshoe weirs. Their key feature included that we are dealing with permanent, man-made permanent structures with a horseshoe shape, typically 0.5 to 1 meter in height. These rock fish traps were set in stone on quay without mortar and clay. In turn, we are dealing with porous structures. And they operated across a very wide range of discharge from drought to mega floods. Also, the fishing operation will typically be restricted when the water depth range from 150 mm to 1 meter maximum. Physical modeling was performed using generic rock fish trap structures based upon an undistorted Froude similitude with a geometric scale from 5 to 1 to 20 to 1. 3 different open channel flumes were used with internal width of 0.4 or 0.5 meter, and using a very wide range of discharge from less than 1 liter per second to more than 100 liters per second. Because of this very broad range of discharges, different discharge measurement techniques were used, ranging from volume per time for very small flow to venturi for the largest flow rates. In addition, pointer gauge and Prandtl pitot tube were used and complemented with video observations. 2 sizes of rock fish trap model were used, as illustrated on the left. And for the smallest size, 4 different porosity were tested, as highlighted on the right. Also, the focus of the work was on the foreground porous structure, which was the closest to prototype rock fish traps. Different flow patterns were observed depending upon the discharges, and the flow pattern was strongly related to the ratio of the inflow depth to the structure height. In very shallow water flow, as illustrated here, we observe a marked Van Kierman street of vortices, with the dye injection here highlighting the vortex shading. With increasing flow rate, while the structure remains still unsubmerged, we observe a 3-dimensional pattern with a strong recirculation and differences between impervious and porous element, with a more stable recirculation cavity with porous element in presence of seepage. This video highlights such an unsubmerged structure with dye injection in the recirculation and the horseshoe free surface profile around the element. With submerged horseshoe element, A three-dimensional flow pattern was observed with a rapid acceleration of the flow above and around the horseshoe structure and shock wave downstream of the structures. This is highlighted on this movie, where dye injection upstream and downstream of the structure will highlight the different flow features. With here dye injection in the shock waves. Measurement of the inflow depth or upstream water depth were performed across a broad range of discharge and are shown here as a function of the dimensionless discharge, within this graph the blue data corresponding to the channels without rockfish trap models, and in red in presence of the rockfish trap models. And of course, the data here highlight a greater inflow depth because of the presence of the structure. In turn, we can derive the afflux, that is the difference between the upstream and downstream water depth, as a function of the discharge, with the same legend, and the difference between the blue and red data corresponding to the afflux caused directly by the presence of the horseshoe structure. Velocity measurement were performed across a wide range of measurement in the larger channel. Here is an example for slightly submerged structures. The velocity were performed with a trundle pitot tube connected to a manometer open to the atmosphere, and both pressure and velocity measurement were conducted. All the pressure measurement showed that the pressure gradient was hydrostatic everywhere, while the velocity measurement highlighted a three-dimensional flow with marked shear zone in the wake of the horseshoe structure. Here, the graph shows as a function of the transverse distance, the velocity measured at 25 mm above the bed and 50 mm downstream of the edge of the horseshoe structure. This graph shows an undistorted velocity contour map at the location as the flow moves around the structure. The data shows the acceleration of the flow around the element, consistent with the converging streamline illustrated with dye injection. Downstream of the horseshoe structure, the velocity measurement highlighted high velocity outside of the element and a recirculation region in the wake of the structure. Recirculation region, which was typically the fishing area, but also contributed to generate a fish attraction wake. The Australian indigenous rockfish traps were fascinating hydraulic structures. They were porous elements operating for fishing over a relatively narrow range of flow conditions, but they were man-made permanent stable structures for much larger discharge. Hydraulic modeling, based upon the Froude similitude, highlighted a broad range of flow patterns with a complicated three-dimensional velocity field. The physical modeling emphasized or highlighted the significance of the porosity for both the structural and hydrodynamic stability. Thank you.